Good morning, and it is Memorial Day for those in the U.S. Um, you know, days off are kind of when I get a chance to do these things. Today we are going to be covering um, kind of a different aspect from what we have normally. This is not going to be a focus on any technology. It's actually going to focus on resources that are available to you. And I'm going to start with a case study from the 1990s, from when I initiated some of this work. There is a spot for questions. I have it up in the background here, so as we go on, feel free to ask questions. I will get to them as I go on. This is your session to learn certain things that'll help you out with your job. The other part we're looking at, this is the biggest part, because my work through my career from 1993 on has been focused in the area of utilizing energy and emissions as a KPI. So you'll notice with the technology aspects of what we do, that there's always that built into it. This is a thing, and to be quite blunt, almost every program we've put together continues to this day, including the stuff that we had put in at a large automotive company that even through 2008 continued on afterwards, just under a different umbrella. So what I'll talk about today is literally how you can pull your program in and tie it to the C-suite through an area of the P&L that your management, from the plant manager to the board of directors, pays attention to, and that is energy. And then, of course, there's the aspect if your company has an emissions portion to it. Everything I'm going to show you today are free tools. If those types of things turn out to work well for you, then you have the ability to look at other technologies, look at commercial technologies, et cetera. And we'll kind of cover that towards the end. I'll do my commercial at the end. So I'm going to start now with a project I did, and it was for the Illinois Department of Commerce while I was the senior research engineer at the University of Illinois Energy Resources Center. So this is where we were literally putting to task everything that I had been developing over the years, along with a large group of others in the challenge programs. All of that information is still available in the public domain. So everything that I'll talk about, I'm going to show you exactly where to go to get it. All of that is there. It provides resources, software, you name it. We've upgraded some of the software I'll mention in this presentation as well. If you have any questions, again, ask. I'm just watching people join now. So I'm going to cover the case study first to show you why maintenance has an impact. And yeah, so part of what we did too was a series of studies. I've upgraded this part here because this was the last time we did the survey. In 2003, the newsletter I have is called the Motor Diagnostic and Motor Health newsletter, because this is when I changed the name. It was a large study, it was global, and we found about 3% of organizations, and we're talking about good-sized organizations, even viewed energy as a reliability metric. Later in 2013, after the crunch of 2008, that became actually zero. And what was kind of funny about that is everybody kept relying on, cost avoidance. And I'll tell you this right now, cost avoidance, I've always termed as a joke. It's literally doesn't tie anything to anything. It's just like the term simple payback. An accounting department doesn't pay attention to simple payback. They give it to us because that gives a flag, but it really doesn't get into all of the ROI and everything else that we need. And as a matter of fact, to go even further, a lot of the KPI that we use in the reliability and maintenance world actually don't even tie to the C-suite. Most managers that I've met don't have an idea of what most of those KPIs are or how they're calculated, because they don't look at the outbound side of what's going on. So your C-suite is supposed to be looking out towards the customer, and as you get inside, you go from there. And I'll have a few anecdotes about that from my time in the military, which included, well, my favorite one is Captain Purcell when I was on the pre-com unit, Theodore Roosevelt. When we met, I was one of the first 100 on board. And so he basically said, if I have to be worrying about what you guys are doing for your job, I'm not paying attention to the mission of the ship. So it becomes incumbent on us to take a look at things. Now, why is all of this important? Why is reliability part of our energy improvement program and vice versa? And here's a neat little fact. This is actually put out by Rochester University back in 1997, that a predictive maintenance program alone, or actually any type of maintenance program alone from a reactive program, will improve energy costs by at least 14%. And what I'll tell you is each program I've been involved in on the electrical side, I've seen reductions from 25 to over 50% in energy costs as you start just doing what you're supposed to do in the first place. And energy related improvements can be quickly documented, meaning instead of saying we avoided a cost, you can literally take a measurement before and after and show the improvement. And that's key. These are not magic technologies. You don't have to be using my stuff. You don't have to, you could literally have a kilowatt meter, or even more so when I show you some of the software after we do this presentation. They've got two. One's called MEASUR, without an E, and the other one's called Verify. Those are both U.S. Department of Energy software, free to download, and Verify will keep track of the energy consumption in your facility and can be tied directly into that, as well as taking care of pulling in some measurements that are sometimes challenging to get. And the other one, you can implement different ideas for your maintenance program or reliability improvements, model it against the U.S. Department of Energy set of models and calculators, and be able to tie an energy measurement to that in order to help you get that project move forward. I'm going out to a customer, we're heading out right after this for an on-site for the next 2 days, because we had been there a couple of years ago and we identified a lubrication issue with electrical signature analysis that was causing an increase in motor consumption by several kilowatts. Came out to be about $5,000 a year worth of energy, solved it with a few squirts of grease. So they're calling us in because they're having other energy problems. And as we know, and here's what's happening right now, MEASUR and I'm going to call it wrong, but PJM and several of the other operators in the area have already done their bids. We're going to see energy costs increase in the Chicagoland area, upward and northeast, the mid-Atlantic region in the US, of between 25 and 50% next week. It's going to be a sudden increase because the bids on available energy went from an average of $68 per megawatt day to $680 per megawatt day. And if you don't realize that's serious, that's average across the board because of all of the increase in energy consumption, primarily driven by our friends that we're using right now, called the data centers, especially the AI stuff. Right now, we're 7.5% of the electrical energy consumed in the US goes through data centers. We're expecting that to hit 15% by 2030 and 25% of the total energy consumed by 2040. And here's the fun part. I'm part of the Seagray grid project. We don't know what to do. We don't know how to get it there. So that's all in works right now. That means that we're going to have problems getting electrical energy out places. So that's why the costs are going up. So let's get into a case with that we did. This is all real data from a corn miller. This one was in central Illinois. We can do things to estimate energy costs from looking at things like the plant airdrop. Now, if you are interested in this type of information, I just put it up on the blog, the vlog. You can go to MotorDocAI.io, and the last vlog, go in there. I'm sorry, 73, not 74, 73, and there's a link to the entire study that you can download, and all the calculations, how we got this stuff, it's all there. Packaging airdrop. So if I have an airdrop, these are DOE calculations, meaning that they may not be what I would do as an engineer, but they are definitely solid pieces of information. So an airdrop in this case, we had taken measurements on the incoming side of a pneumatic process, and on the out at the end of the line, it was at 45 psi, and then everything was due to numerous air leaks in the system. So the measured power, because we had compressors that were electrical, was 220 kilowatts, and then we can go 0.5% times the actual pressure drop. So it was a 55 psi pressure drop. That comes out to 60.5 kilowatts due to the pressure drop. Now I can calculate from there. You're going to see me do these calculations repeatedly, so I'll spend a few seconds on it. Demand charges, that is the peak that I would use within a period of a month or with a billing period. You'll find this on your utility bill. Okay, that's your cost for the kilowatts used. In this case, we're going to use $14 per kilowatt, which was the real value at the time. And that will be what's called a demand charge. So 60.5 kilowatts times 14 per kilowatt times 12 months. So that's about 10 grand. And then the charges themselves, you need to look at the operating hours. Now your operating hours may not be 8,000 hours. It might only be 2,000 hours. It might be 4,000, 6,000 hours. 6,000 hours is 5 days a week, 50 weeks a year. So if you have shutdown periods and everything else, it's a safe number to use. Doesn't look as dramatic for presentations though. So I'm going to use 8,000 hours in this case. So that would be at 7 cents per kilowatt hour, which was what they were paying. That's 33,380. So that comes out to be about 43,500 per year, just to feed air leaks. Now these will be both audible and inaudible. Compressed air systems are one of the most inefficient systems that we have in any industrial facility. It takes 1 horsepower to make 9, or I mean 9 horsepower to make 1, backwards. So when we take a look at this, 44,000, okay, I must have done something incorrectly here. $44,000, just doing the maintenance practice of fixing air leaks, that's a solid fix. Okay, so this is the same site. This was an interesting one. I've told this story a couple of times about walking into a building in which we had to wear double hearing protection, everything else. There were cobwebs on the doors because nobody approached the building. Well, apparently at some point in time, an operator had decided on this system here, which is 150 psi, it's a 1/2 inch opening, to just open the valve instead of going in there and just blowing it off periodically. And so they left it open. That's a 1/2 inch air leak in a 150 psi system. To put this in perspective, they had a cogen unit on site, and when we closed the valve, we could actually watch the kilowatt meter move. The solution to it, by the way, was a $1,000 automatic blow-off valve. So, but to put it into perspective, losses through the opening, there are calculations to come up with the CFM. As a matter of fact, in the MEASUR software, And then the demand, that comes up with a demand loss of about 120 kilowatts using 150 PSI and that value. 120 kilowatts times $14 per kilowatt times 12 months, 20,000. And then that energy consumption comes out to be 87,000. Basically an immediate payback just by putting on a piece of equipment that they needed. And then they were able to start doing other maintenance, which actually reduced their losses even further. Then, of course, we'll get to electric motors, of course, right? Everything kind of electrifying and so on. Some of the things we noted was they asked us to look into why they were having some electrical problems. Let me put this into perspective. Motor-rated fuse, not motor-rated fuse, lighting fuse. So yeah, when we opened up to do our monitoring, we caught that right away. And, you know, is this a one-off? No, we just ran into another one just last month. So it happens more often than you think. Putting in the right fuses and things like that are going to save you a lot of problems. We're going to cover pumps in a few minutes because that was another big area. So loose connections, that's an I²R loss. Now, here's what's interesting. All of your combined I²R losses, meaning the stuff you'd pick up with infrared, and other conditions in your system, including low power factor, have a total opportunity of a 2% improvement. That's total, not I²R, not this, that, and the other thing. But if I get up to a system where this was, I don't have a picture of it here. I lost the infrared picture some time ago, but we had what we measured as a 0.5 ohm loose connection. Yes, you could not go anywhere near the cabling. It was so hot and it had embrittled already, but it was a very, very loose connection. It was just shy of glowing, literally. That 0.5 ohm connection on a 100 amp circuit comes out to be 100 squared times 0.5 ohm. That's 5,000 watts or 5 kilowatts, the equivalent of about a 7 horsepower motor at that one point. That came out to be an energy cost of about $3,600 a year. When you start looking at plant-wide, slightly loose connections, it could be a fraction of this, less current, et cetera, et cetera, et cetera. It's always I²R, by the way. It doesn't matter what the voltage is. It's the amount of current passing through a point and the resistance. People forget, everybody keeps talking about voltage and stuff like that, but even in IEEE 519, which is a harmonics thing, and I'm not going to touch too much on harmonics unless I have some time at the end. Harmonics have an opportunity that is tremendous now because of all the electronics we put in place. In 1995 or 1997, it was determined to be 2%. And that is before all of the electronics we put in place. Now everything is electronic. So we're seeing improvements exceeding 10% in most facilities just by cleaning up grounds and neutrals. It's amazing. For those who've watched that stuff, I've been applying it or recommending it. We don't sell it or anything like that. Somebody else does. And, you know, it's been amazing. 32% at one facility. Variable frequency drives. Back in the day, we were replacing a lot of DC equipment with AC. We're seeing less of the transition. As a matter of fact, the total population of electric motors based upon the 2021, so not that long ago, 2021 manufacturing survey by the US Department of Energy, 20% of the motor population is still DC motors. Steel plants, aluminum plants, things like that, all use DC. Heck, we go into wastewater and water treatment plants and still find a lot of smaller DC machines. And just so you're aware, 96% of the electric motor population is 25 horsepower and below. and the remainder is above that value, with less than 1% being your medium voltage machines. Yes, you end up with fewer losses in the total system and everything else. The challenge we run into with variable frequency drives is the introduction of harmonics, because the majority of people purchase these things and put them in place. They've either been sold on the fact that it's a clean drive, or they've been sold on the fact that you don't need to put in filters, et cetera, et cetera, et cetera. Plus, the grounding on these systems will often put a noise into the ground. We just did a survey of a plant in which we saw, let's see, the phases were about 300 amps each, and there was over 100 amps sitting on the ground. So that was a significant issue. So there's things you have to be aware of as you go through variable frequency drives. Now, electric motors, repair versus replace. Now, back in the 1990s, we got most of the older efficient motors replaced with energy and premium efficient motors. We also had a few other programs going on where you could get payback on that. That does not happen as much anymore. Instead, you need to take a look at repair versus replace. So these calculations here, which will be in the documents that I show you, the improvements are not hugely significant when you're going from a premium to an energy efficient motor, but you also have to consider each rewind can reduce the efficiency of the motor by 0.5 to 1%. Now, I've seen documents claiming otherwise, and there's a long story behind that, but in reality, IEEE 1068, which is the motor repair standard, the motor repair industry pushed a 20% allowable increase in core losses, which equates to between 0.5 and 1%. So as you look at the repair versus replace, you have to consider whatever's on the nameplate, which is already the average. And believe me, for whatever reason, most manufacturers, average actually means the highest. You're going to find that the values tend to fall slightly below that. You want to consider each rewind and reduce that efficiency. And most of the time on older motors, say if it's an old T-frame, just a straight motor or a U-frame motor, that you're only going to get 2 or 3 rewinds out of it before it really becomes more of a heater than anything else. If you want to get an idea, you'll see just with a plain clamp-on ammeter, you'll see an increase in current for the exact same load before and after. Used to be a trick we did for a repair shop I was involved in. You'd go in, the exact same load, exact same settings on a 100 horsepower motor. You knew that the core losses increased by clamping on and seeing several amps increase in energy, not energy consumption, in current draw. The kVA went up. If I took a kilowatt meter, I would see a slight increase in the kilowatts. So this stuff here is actually off of something called MotorMaster Plus. You're seeing that I make mention of it here. That was an old software. Best it worked on was Windows 7. After Windows 7 went away, so did the software. Luckily, the Department of Energy under Oak Ridge National Labs took all of the different software programs we developed and put it into an open source system. As a matter of fact, for those that want to build it into something or whatever else, there's not just APIs, but the actual program, the code, is available for those who do programming on GitHub. So yes, you're going to see something from us soon. So let's get back to that a little bit. I had a whole bunch of industrial engineering students. We had 7 of us that did the project because I didn't have a lot of funding and we wanted to do something really in depth. They won every engineering award that year, and all of them walked away with like $15,000 apiece in their pockets from the awards. The idea was to build a model. It's actually a model that's been partially adopted by DOE. And then we were looking at a combination of energy, waste stream process, and reliability and how it all interacted. I did put the last vlog I put up was an AI generated vlog of that process. I'm sorry, vlog 73, not 74. We did a combination of modeling, which we now call digital twins. Believe it or not, none of that is new. I was doing that kind of work, as a matter of fact, taught that at UIC back in the mid 1990s. So none of what we're learning about now is new. I'm a strong proponent of all of those practices and the ability to use modeling. I have certain cautions. So if you listen to any of my stuff, some people think I'm a little negative about it, but it's not. That's not the case. I have to. I'm one of those model, figure it out, do a test application, and then a full application. Don't just go from modeling to end. And then anybody who's involved in that has to have real experience with whatever you're modeling. We're not teaching that anymore, and the results are pretty apparent. So what we wanted to do is select a set of tools, and we ended up selecting tools, and ASD Master, Pump System Assessment Tool, Motor Master, also STEAM and everything else are all available from the DOE. As a matter of fact, they'll be in the software that I'll show. So we took a look at taking that stuff. What we found in the end was opportunities in average of a 30% improvement in processes, 10% and 10% waste and energy improvements, et cetera. The students did their test on a 5,000 square foot bakery. We went way beyond that. We were applying these on power plants to corn millers. So in the end, across all industries, we found 40% production increase, 66% reduced waste, 3% effectiveness, and 6% energy. Production schedules had an impact on energy and reliability, material levels, ergonomics, workflow, and reliability. When we went back to the bakery, which was a small bakery, they made lemon knots and carbolitas for one of the big coffee chains. We went through and we had the industrial engineers remap everything so they weren't running into each other, et cetera, et cetera, et cetera. One of the biggest opportunities there was they had been emergency repairing their cookie cutting machine. I don't know if that, I mean, small place, main machine. They had somebody who ran across the street. There was a hardware store across the street, ran across the street, got an English bolt to put into a metric fitting and stripped it. And basically several times a week, sometimes once a shift, they ended up having to repair the machine over and over and over again, and they'd lose anywhere from 30 to 60 minutes. Fixed it with a drill and tap. So that was it. Which basically I had in a toolbox in my car, so didn't cost anything to fix it, and off they went. So one of the things we came out from that, and I advised the students at the time, don't sweat the small stuff, get an overall evaluation of the plant and opportunities, and then focus on the true issues. Basically, don't worry about, whenever you get an engineer involved in anything, we like to dig and look for the minutia. We had engineers, they wanted to know details like how much sugar was in a cookie, and I go, what on earth does that have to do with the goal that we have here? None. We need their energy bills, we need the location for temperature, so that we knew heating and cooling stuff. We needed overall production values, like how many pounds or tons of cookies came in, how much raw materials came in, so that you could look at the losses coming in and going out, because in food processing, anything that hits a certain point is not human consumable, so we'd refer to it as pig slop. So getting back to that other study, the grain and corn miller, that is no longer owned by Midwest Grain Products. We did have the really cool bit where we had 2.5 million gallons of 96 proof bourbon. Figured if we went swimming, we'd dissolve, but it was a really cool idea. This is their cogen plant here. We're standing on top of basically the cooker. We did talk about this briefly. That was that compressed air system. Back to this one, we did an overall motor survey of the facility. One of the big things we did that was good is we did all to get the energy and reliability part is we made all the decisions on the motors ahead of time. What was available, what needed to be inventoried. 91% of their electrical consumption went through motors, so that was a big deal. So we took a look and saw if there were any additional VFD applications that would work, and we preset repair versus replace options. So they coupled up with a vendor for electric motor replacement, and then also outsourced the storage program, because most of their stored motors were completely useless by the time they went in place because they were in a bad environment. Steam leaks, these are actually money as well. So if I just see plumes of steam drifting around, that is a huge opportunity, especially with natural gas. Steam leaks, excess steam, meaning, what we were looking at is the steam blow off here. That's about 20 pounds. From their high pressure steam. This is the remainder, whether or not that could be recompressed as part of the process. So when we were done, steam traps, 10% of steam traps fail per year. And in another case, we came up with a way to reduce the impact in automotive. It's applicable elsewhere. They have, there are steam traps that are live swappable, meaning you shut some valves, you pull out the old one, put in a new one. That reduces it and allows you to use things like your ultrasonic, infrared, and other tools to identify good and bad steam traps. That's an impact. Leaks alone, again, leaks. That's a maintenance aspect. Both of these is that this is a production impact. So can they reuse that steam? Or does it make sense to just let it blow off at $186,500 worth of natural gas cost? Now, lighting retrofits, and this is interesting because in a recent project, we started discovering that LED lights increase your cost due to a significant impact on harmonics in the system. We just did a study at a plant, and we were monitoring for a different project. So we were looking at the actual, so when I do an M&V project, I look at I do what's called a Class C, or we look at the actual energy meter from the utility. So we get that utility data, which you can get, especially in the US, in quarter or half hour increments. And then we were able to use that and then tie it to things. And so when they did a lighting retrofit from T8s to LED, we actually noticed their energy consumption in the same conditions went up 1.5% due to harmonics. So lighting demand, I'm sorry, that's in this case. So here's what I usually do when I walk into a facility if I've been asked to participate in an energy project, and we do quite a few of them. First thing I do is walk in the door and I look up and I see what type of lighting they have in place. If they still have T12s, if they have, and it's not, sometimes people will have, of course, lighting systems up that are meant for aesthetics. I ignore that. I'm looking for all of the energy. If they went to LEDs, because that's perceived as an energy project, that's the number one thing you look at to determine if that company is going to even consider applying what you recommend. So if you walk in, you can tell if they're lip service or real by looking up and saying, okay, they put in T5s or they put in LED lighting instead of fluorescent. They don't have incandescents, which are coming back, by the way. They have all these other things in place. So they're taking it seriously. Then you know that they're going to be paying attention. Always put that in there. So back in the day, 300 kilowatts worth of lighting across that particular facility, we saw what amounted to a 1.7 year simple payback. So other waste stream stuff, product leaks. Okay, there was literally how we measured how much bourbon or alcohol they were losing here off this pumping system, and there's literally a rag wrapped around that with a chain fall wrapped around that. That turned out to be a 5-gallon bucket per minute. So if you've got produced stuff that you've already worked on and you're filling up, that's definitely a loss. Same thing over here. This is a different leak. So they had leaks all over the place. Maintenance, right? So lost product or lost product. So that would have been more product that they could sell to get flavored in Kentucky to sell to everybody as bourbon. This was a biggie here. I don't know if I have this in a slide. There's only a couple more slides I'm going to cover, and then we're going to get into the tools. But this is the mash pump. So a buyer made a decision. So it wasn't an engineering decision to go from a double cartridge seal to a single cartridge seal. So because they were replacing these every 12 weeks or so, swapped it over to a single lip seal to reduce the cost for the every 12 weeks, and they were replacing them now every third week. And the maintenance staff got so tired of replacing them that they just stopped. So nothing was in there. In this case here, they're dumping water across the shaft to get the mash to come down and then go into the sewer, and then that sewer goes to an on-site wastewater treatment plant before they can put stuff back into the river. So it's got to be cleaner than when it came out of the river. So basically, they're putting stuff through waste processing, causing that side to work even harder. So we had actually put that together, and a majority of their process involves pumps. And in the mash side, that came out to be about 15% of their electrical energy consumption. And then when it hit the wastewater treatment plant, it actually doubled the consumption there. So that was a significant find, and our recommendation was go back to the double lip seals so that they can be replaced. And then we had a seal company come in to look at what would fit that application better. So here's more examples of that. Yeah, there's the last only 3 weeks. To replace all of them was an 80. That was their cost to if they had been replacing them. But everywhere we went, there was leaks. Okay, process heat's another thing. I'm not going to cover that right now. Their cogen plant was actually there to produce steam, not electricity, and their cost was $4 per 1,000 pounds of steam. And then they also used it for electrical energy. It was operated by the local utility for them, and it still cost them a certain amount because of all the costs associated with it. They didn't ever have to export any of that power. A couple other things. This is an example of what we see when we do the walk downs. There is a bare wire touching that. This is so rusty that when I tested one phase the surface of the motor to ground, I had right around 200 volts. This was right outside that hallway right there. That's the electric shop is there. So the electricians were walking by this pretty much constantly. This is something where I would say, it's often of benefit to have a third party do a walkthrough. Now, those could be industrial assessment centers with a DOE, that would be students and professors for a 3-day walkthrough. That could be a consultant that's familiar with the systems, things like that, to walk through and get an idea of where the energy opportunities are, but also some of the maintenance opportunities. This is one of the reasons I push back hard when we want to go straight IoT stuff and ignore everything else, is you won't see this type of issue necessarily. This is something that could have been identified visually. In the meantime, yes, the connection box had water in it. We did a whole bunch of other studies as part of that program in order to prove it out. Yeah, so I'm going to skip that part and we're going to get into the rest of it. No questions so far. Just trying to take a quick look and see who's joined us. Oh, hey, okay, cool. This is recorded, by the way, and we'll have it up so you can view it later or show it to your friends. We're going to get into the fun part now. So back in the day, we had, back in the day, I always wanted to say that, now I'm old. We in the 1990s, due to the Energy Policy Act of 1992, there was a large amount of funding that went into the Department of Energy for what amounted to partnerships with industry. Those were referred to as the challenge programs, and they went from 1992 until 1997. Then they were rolled into one program. So during that period of time, that 5 years, there were teams, Motor Challenge alone, there was about 70 of us, roughly. Repair shops. I was at a repair shop, ESA, a bunch of other organizations, OEMs, everybody. 3M was a big participant in most of the challenge programs, looking at ways to reduce their energy costs. Well, we're right back at it. We're going to see significant energy cost improvements, or increases, I should say, not improvements, as a direct result of certain things. This also happened in 2004-ish, when natural gas prices increased. And I made a call from General Motors to a friend of mine at DOE, and that afternoon, the Secretary of Energy came back to support General Motors, and because they couldn't support a single entity, came out with the Save Energy Now program. So General Motors was actually the first organization through the Quality Network Plan Maintenance, that was a joint union and management team at the time, to adopt all of the US DOE practices. Now, the QNPM program that I was involved in, that I was a consultant for, we were the maintenance program. That means that the entire energy program that was launched through that, this was in parallel with an actual facilities energy program, was strictly done for the maintenance perspective in order to tie maintenance directly to costs. In fact, the potential savings we identified, we were advised that we almost exceeded the annual energy costs, or energy budget, I should say, because it wasn't accurate. The energy costs far exceeded the budget. So we were looking at recommendations that were 30 to 40% of the total energy consumption by facility that was surveyed. There's several articles on it that are out there. In any case, let's go ahead and we are going to take a look at a few of the programs. So you notice energy.gov. Whenever you see .gov, that's actual government. So EERE, which is the Energy Efficiency Resource, whatever. I forgot what it stands for. It keeps changing. Matter of fact, this keeps changing. So what I usually do to find it, I don't know why government wants to constantly change everything, so they keep changing the location of the tools I'm going to show you. So putting in, or starting at, Motor Challenge, for instance, the US DOE will get you right to where that stuff is. We'll cover that here in a second, because it won't be just motors. It's going to be all of the other tools as well: plant-wide assessment, steam, process heating, combined heat and power, etc. And this is just document upon document on how to make improvements. And this is why you hear me talking about energy and emissions and stuff like that. And I have since the 1990s. We discovered back then that retrofitting motors and going to more energy efficient systems and all this other stuff had very small impact on the overall energy consumption in a facility. What did have an impact was the maintenance programs. Yep. So I buy a new energy efficient piece of equipment, I put it in place, or premium efficient, or quadruple, super duper, whatever efficiency, and I put it in place. It's worth nothing if I don't maintain it. it's going to eventually degrade. And you want to be able to come up with means and methods to maintain the operating efficiency of that equipment, let alone if you are going to fix, repair, or upgrade, be able to determine if that fits the application. Okay, so this one here, this is the Industrial Technologies Office. That really hasn't changed since 1998-ish. This here goes through and it comes up with different types of opportunities. Okay, so yeah, informational primarily. We're gonna skip this stuff in a second, but it's all about assistance. Okay, Industrial Innovation Research Database. This would be innovation projects for making improvements, et cetera, et cetera, et cetera. Some of that is product, some of it's process, and a lot of it is energy and maintenance. So for the next couple of minutes, I'm going to show you some of this stuff, and then we're going to spend the last hour or less going through and showing you measure and verify. And you'll notice here, Energy System Assessment Tools, the Measure tool. Okay, free to download, automatically updates. It survived all the program cuts so far. DOE is actually getting quite a bit of funding. So technical publications, these are the things that we created. Some of them have been updated, like I believe, yeah, these should be the newer ones. So let's click on this and we're going to pull it up. Yeah, so let's zoom in a little bit. This one was redone. When did we do that? There I am. This one was redone in 2010-ish, or yeah, about 2010. And it goes through all the components. It basically, all the best practices, all the different notes and everything else goes through this stuff. It's written in a way for people to understand, including definitions. Let's hit an example. Okay, so how to start a program. So say a motor program. And this is where back in the mid 1990s, my 1997, I published it as my master's thesis, was the motor management program. That included motor storage and everything else. A bunch of companies adopted that and actually do it as a business. The company I was working for at the time did not. So basically a lot of definitions, how things work, you know, what the concerns are. There's even stuff on how to perform maintenance practices, procedures, things like that. So let's go back and then we'll take a look at this one here. This one is, let's see if this is an updated one too. Of course it is, and you can see I've already read it again. There we go. This was another one that we updated about that time. Yeah, they put me at the end that time. So this goes through the premium efficient stuff, precautions you have to take and everything else. Good guide. You don't have to read it start to finish. You can go through it. So here's the big section here. Okay, so I think we had included some other stuff in there too, but basically including also how to troubleshoot different conditions, et cetera, et cetera, et cetera. You can notice a big emphasis outside of definitions and applications on steps to maintain things. So let's take a look. Let's say belted power. So in here, it just basically talks about how often, what to do, and then the improvements and et cetera. Now, is that the end all? No. As a matter of fact, if we stick with belts, because I love belted applications, they make me lots and lots of money. Oh, yeah, like this one was an interesting one. But as you go through, how to buy, these are all the things: replacing oversized and underloaded. Where's the one I'm looking for? And then motor repair tech brief. So model repair specifications. This was adopted by ESA later, and it goes through basics. This turned into the yeah, you can get an idea how old this was. This would have been 1999. So I was at BJM or All Test at the time. It's an overview of how to perform a repair. So what ended up from this was both the ANSI ESA AR100 series and of motor repair, and also the IEEE 1068 came as a direct result of this. So you can see the different repair processes, et cetera, et cetera, et cetera. All the stuff, all the concerns, all free to download to take a look at. We're an ESA member, so if you're interested in the AR100, let me know. Determining electric motor load and efficiency. Can you do it in the field? Yes. As a matter of fact, what it does is gives you multiple methods of approaching and taking measurements to estimate the load and measure and estimate the efficiency. Okay, so you can do that with voltmeters and ammeters. You can also do it like the way that we do it with like the empath, is you take your data and you get it in actual watts. Okay, so here's the simple calculation for how you can come up with input power versus output power and the result in efficiency. So it gives you, I think we determined it was about 1.5. It would give you plus or minus 1% efficiency basically, versus the more complex IEEE 1068. Okay, when to purchase, estimating motor efficiency in the field. Okay, these are tip sheets. This one, there was one on belt alignment somewhere. I think it might have been incorporated into a book, into one of the books. Yeah, you can see I tend to do these seminars based on what I know is there, and sometimes that isn't there. Yeah, these are the old ones. And let's take a look. I think there's one somewhere on alignment that goes through what the potential energy cost is on even alignment. And I believe that also that must have been put in place as part of the rest. So here's another one here that's pretty important: eliminating voltage unbalance. Voltage unbalance has a very definitive impact on the efficiency of the system, as well as over and under voltage, which is a separate one. And it tells you how to calculate the losses associated with it. You know, little things like that. So these are great tools. We're going to cover this in a minute. Let's take a look plant-wide. And by the way, this subscribing for updates, that's pretty consistent. Let's see. Looks like I might be having trouble keeping up. So I'm going to turn off my view here for a second. See if that improves the stream. Okay, so plant-wide, a lot of these are relatively new. Some are not. So the first one here is lighting. These are case studies on, so people go, well, did somebody else do it? Yeah. There was a lot of work done to work with other organizations. So you can see, you know, by name who's there. We'll come back to that one in a minute. Steam, this is a big one. Going to give the audience view thing a chance to catch up. There we go. Okay, so you can see there is a software program called the Steam System Modeler. You actually can lay out your steam plant and run different models on it. And I believe that you can also have inputs to it from your own system. So different things having to do with steam. Okay, I wasn't as involved, but here's that one, inspecting and repairing steam traps. So this is an explanation of how to do it and how often to do it. Sure, I don't lose anything there. Technical publications, this is all free to download. Okay, so let's go over and take a look at compressed air. It's a big one. So you can see the old tools are still there. The AirMaster tool and log tool. They won't work on won't work on Windows 11, that's for sure. But a lot of the case studies, a lot of the calculations and everything else are here. And there's enough information in many of them to help you put together steps to make the improvements. And then when you subscribe, government, if you put in the thing here, it's gonna keep you up to date. I get that periodically. There's a lot of really interesting information that comes in. These are, I think so. Yeah, these are also pre-recorded. So let's take a look finally at, let's go back to the measure tool. So give everything a second to catch up. There we go. And I always tell people, sorry, that as soon as I hit midday, it appears that doesn't matter because I've got two facilities next door that have automated stuff and they leech off of my account. Not their fault, just there's a limit to what's here from Comcast, and Comcast tapped into the system I paid for, but neither here nor there. So here's a list of software tools. So some of this is online, that's relatively new. Here's the legacy tools if you want to go get the originals. Now, let's see if they have the VFD one. Nope, they never updated it. There was one on variable frequency drives. I have a copy somewhere, still works. It walks you through and develops a specification for VFDs. So I think that was sold or licensed to somebody who's made it commercial. MotorMaster has been licensed to somebody to make it commercial. It didn't really. There's also an international version of that, which does still work, but you don't need that because of the new system. So all of the modeling tools and everything else are here. Let's go up because I'm interested too. So here's the link to GitHub, the measure tool, using the tool online. That's new. I just want to see it. Yep, it's the exact same thing as using it offline. So we're going to use it offline because that will just dog me down. Okay, so let's take a look and see what's here. Oh, just explanation. Okay, so we're going to get into the software then. So I am going to minimize this and I am going to drag over a couple of things. If there's any questions at the moment, please feel free to ask. So I already have them installed. What I did do this morning is zero them out. I updated them last night. I do use them on occasion, so they're always on my computer. Let's cover verify first. Okay. Because we always wonder how we can do this. Now, this will involve working with the accounting department for your company. But the nice thing is it's got certain features. So I had removed everything. So set up, I'm going to do the automatic one, but let's go ahead and say you come in and you can set up your information for your company. You set up individual facilities, and then you can do a confirmation and tie your actual accounting system, your energy system to the software, and it'll keep everything up to date. Now this, because most companies don't want everybody in the company to be aware of their costs, this could be done by your accounting department. Okay, so we're going to do the demonstration. Now it's putting in all of the information and everything else for me, and looks like it's conflicting with my audience view. So no questions so far, huh? Okay, so real quick, some of the things that we do is when we go out and we're taking a look at applications, we do everything we can to tie the energy costs into that program. So we'll take a look at the if we don't have the direct energy costs, we'll get an average, and we will or we'll use some dummy number. So easy ones are 10 cents a kilowatt hour and $10 per kilowatt demand. That makes it easy for somebody who knows the actual cost to modify it a little bit, because it's a factor of 10. So if they're at, say, 14%, that would mean 1.4 times the value, et cetera, et cetera. This is taking just a bit long. Might have been a bad idea. It's downloading stuff. So hopefully you can hear me. Do me a favor. Can somebody just type in if you can hear me or not? Perfect. So because I'm getting an audience view thing that's telling me that things are really choppy or not doing a great job uploading. So hopefully this doesn't take as long as it appears it's taking. So while that's happening, I am going to go to measure. See, I think I can get to measure from here. Why not bog everything down? So while that's updating, let's take a look at MEASUR. So this is the other software. You can see I reset it. It's going to walk us through a few things. Okay, so these are basically how to model different type of applications. We'll walk through an example. We'll do motors, and then you can take a look at any ones that you set up. You can also go directly to calculators, and these are engineering grade calculators. Okay, so Mark, you're asking me about energy losses through ground and neutral. It is actually not that simple because most of the losses are now through high frequency and ultra high frequency harmonics. So they can be anywhere. I mean, we're limited to 22 kilohertz taking a look at things, and we have the only one able to look in the super harmonic range at this point. So up through the 50th, that's simple and straightforward. You'll see a lot of third, fifth, etc. Anyways, let's get through this real quick. Manual, links, and so on. So here we go. Let this open up. And we'll go ahead and get started. So here is the MEASUR software. And let me cover this question real quick from that showed up. So through ground and neutral, yeah, you have to use something that will display the waveform. So you do want either a harmonics meter of some type or an electrical signature analyzer that can at least look out far enough. You want to see it minimum of out to the 50th harmonic, because the actual measured current, if I go on there with a clamp on ammeter, I might measure a couple of amps, but when you take a look at the peaks, those can be much higher. So for instance, we went to a site and a clamp on a true RMS clamp on ammeter, which is a really bad idea for doing power quality measurements, clipped on, and it was telling us 1.5 amps. Well, the peak current was actually 27 amps, and that's all in higher frequency ranges. So it was a really not pretty looking waveform, and the end result was their energy consumption was actually much higher, not just from I squared R, but also losses in the transformer, et cetera, et cetera, et cetera. So the ground itself becomes a load. When I get above 60 hertz, when I hit third harmonic on up, any capacitors I have in the system become loads because they're tuned to the line frequency and so on. So let's take a look at some of the stuff here, and we'll go through what this is. So I just downloaded, so this is 1.5.12, and then this is to subscribe, etc. So coming here, examples. So we'll cover some examples, and then the calculator. So let's do the calculators first, just so you can see what the calculators look like. Okay, so general calculators are like just converting units and energy. Let's see if I can pull one up. No, not just energy, basically all kinds of unit conversions. That makes us, let's just say it pays for itself already. Combined heat and power, we'll walk you through, this is cogen, basically. Cash flow. Now, this is what I like to use when I'm evaluating conditions. So let's say, let's generate an example so we don't have to sit there and do it. So here we go, 15 years for the life of the project. Annual energy savings is this value you can put in other savings. The salvage cost when you're done is this. The installation cost is, in this case, $250,000. Annual operating costs, $5,000. Other annual costs here, say maintenance, disposal of the system is this much. The discount rate that you would get from your accounting department, that all goes in, and then it produces present value, annual worth, and then so the net present value. So basically the information, so here's your simple payback, 5 years. But let's say the hurdle rate is 20. So my internal rate of returns at 16.8. So this would be something that's a little on the low side. But as I go through, this is information the accounting department can use to determine if there's value to it. Okay, so the operating cost here, and you look at the before and after, and you come up with whatever. So all of this information here is what's needed for the accounting department to take a look at a project. Okay, so let's take a look at, so that takes over, whoops, made a mistake there. That's not what I meant to do, but Let's go back. We'll hit that after. Calculators, not data exploration. I don't have any data in there. Power factor correction. This will actually tell you how much power factor, what type of power factor correction you need to put in place to improve your power factor. Not a big energy thing unless you're being billed on kVA. Power factor triangle, carbon emission savings. You will usually put in where you're located, and that will end up, yeah, this is in kilograms. I usually work in something, oh, that's natural gas. Energy type, electricity, let's do that instead. Let's do where we are, 60148. And yes, it's going to figure out the losses based upon the latest for us here. So in megawatt hours, let's say I'm using 800 megawatt hours a year. And then it's going to generate that for me. Okay, so there's my baseline. Now, if I come in here and I make an improvement, 60148, there's that same amount, and say I drop it down to 750 megawatt hours, and then it's going to calculate the total energy use, the modification, where I was before, where I am after, and then the tons of CO2 after. So when I do have that value, that helps me out. I can use that from the overall energy consumption, which we would end up getting from here, which is still not done apparently. Electricity reduction, so total energy savings from that, etc. Compressed air calculators. This is everything in the compressed air system that you could possibly want to do. So there's this one here. There's a couple of ones. Oh, this is my favorite, the bag method. So in effect, you take a bag, so it explains it here. You enclose a bag over the leak, and then you put basically a trash bag, and you go until it fills up, and then you basically put in the dimensions of whatever, and it says, say, bag fill time in 30 seconds, and I've got a 40 by 46, and I think there's a metric. I think you can change this over to metric, but it tells me how many SCF or cubic feet per minute, and then the annual consumption associated with it, and then I can go from there for calculations. So let's get past compressed air, fan calculations. So including how to develop the fan calculator, lighting replacements, all of the different motor calculators, okay, including repair versus replace stuff, process cooling, process heating, pump calculators, steam calculators, wastewater calculators. So you can see that there's a lot of things here that you have available that will be able to assist you in providing information to make changes and improvements. So let's go ahead and let's take a look at drive recommendations. So we're going to go from a notched V-belt to a synchronous belt. And let's go off of 10 cents. Let's get a real machine in there. Let's go 150 horsepower, because I've seen one of these recently. And let's say we're at 70% loaded. And then as soon as I come out of that, that's going to give me my difference. Okay, so here is, total savings would be about 3.1%. So here's the energy cost before and after. So the actual savings would be about $2,200. And then this is a comparison down here. So I can go, okay, does that make sense? Copy table allows me to copy it and put it into like Excel for description. Let's go ahead and do one more example, then we'll get into, just go to motors. Let's do a repair versus replace real quick. Okay, operating hours, 8,760 means round the clock, 7 days a week, 24 hours a day. Here's that same motor I just put in, 150 horsepower, 75% loaded. I haven't upgraded that part yet. That's in settings. And then the efficiency of the original motor. So let's say this 150 horsepower motor has been rewound once. So let's just say 91.5. We can adjust it. The efficiency of the new one is 96. Purchase price, let's say, because we got all this stuff going on, that's now 16,500. And then there's the efficiency loss here. So I don't need to do that. Let's go ahead and we'll just leave that the way it is. Cost of a rewind, because prices have gone up in copper, so it's a 500. Just examples, it's not realistic, but we'll do that. And then as soon as I tab out of it, you can see there's the energy consumption for the existing versus the repaired versus the new motor. So here's my energy cost per year based upon 10 cents per kilowatt hour. The rewound motor, that means it's going to cost me an additional $8,800 per year. The cost savings is low, under $1. New motor, it's going to be $3,800, but the simple payback is 4.38 years. Now I can take this information then and put it back into the calculator for savings, and it's going to tell me some other stuff. So if I go in here, so this is basically the rough, okay, repair versus rewind. Okay, so the sunk cost 10,500, annual energy savings is this, cost difference $6,000, energy cost savings is $46.54 per year, simple payback is a year. Okay, so that is basically, this is the number I'm going to use. Okay, so this is savings compared to the existing motor. So, I'm sorry, this is for a rewound, and this is if I just outright replace it. My bad. So this is the repair versus replace calculation. Sorry, they changed this around a little bit since I just downloaded it yesterday. Okay, so data storage. This allows me to save my data in here and do a backup. Settings, this allows me to go through, it'll do my tutorial and everything, but it's also going to allow me to put in what I'm doing. I can put in, for those who are watching that are elsewhere, let's see. I have had requests from people looking for energy savings for doing better alignments. Talked about this and was wondering if you had a quick link to a study the DOE has done. No, the DOE has not done. The papers I've found selling alignment systems, except for me, I don't sell alignment systems, and I did a study on it. And so did, back when they were independent, I think it was Charlotte and Associates, the vibration folks. They did a direct alignment one. We found that if I meet a standard alignment, basically what's considered good based upon publications and not a precision alignment. Precision alignment, you only increase the losses as far as friction and windage, and that it's also hard to define precision alignment because I don't think there's an actual value for that, even with the new standard. You are talking about 10 to 15% increase in the potential losses of a machine that's not aligned at all, meaning not connected to anything. But as you go to a standard alignment or just meeting what people put out there, I believe it's an increase in friction and windage losses by about 60%, or roughly 2% reduction in efficiency on the motor. So the costs do go up and it reduces the life of the machine. So we do know that part. The DOE had something about alignments. Before we're done, I'll see if I can find it. And it was, yeah, they did have something on alignment. They just put out some generic information though. Okay, so, and then here's your energy costs for that you would put in. So that's why we got the 6.6 cents per kilowatt hour here. And you notice there's no demand charge in here. They're going off of kilowatt hours. So usually what'll happen is people will combine the two and come up with a value for the amount. But so I can come in here and I can change this. Okay, currency just US dollars, but I can change everything to metric for those who are overseas. Emissions results. Normally, whenever we're doing that as a reportable, that is in metric tons. So a ton, an English ton is 2,000 pounds. A metric ton is 2,240 pounds. And then this is also different energy units that we would want to use for stuff, so I can make everything common to whatever. Okay, so for instance, when I was at the Energy Resources Center, we had to convert everything over to kcal. That was also that we would have common values as we went through. The CO2 settings, that just goes by zip code and pulls it off of the eGrid. That is a US EPA system for calculating the emissions. So when they go off of eGrid, that is for your inventory. And then I'm going to show you another little tool for showing savings as well. Okay. So that's settings, custom materials. This is so you can put in additional information. Here's all the user manuals for each thing, and etc. So you saw that thing about treasure hunt. So let's go ahead and let's pull up treasure hunt. Okay. So we come in and we say currency is this, imperial that many. So 8,760 hours. This means that I come in here and I would put in, this is just an example, I would put in my energy costs, natural gas, water information, etc. Put that all in and then come through here, and it will allow me to go through and run different opportunities to see how they would affect you know, so yeah, okay, that's an addition. So these would be individual assessments, but let's say we want to focus on electricity. So electrical reduction, say we wanted to reduce the consumption by a certain amount. Let's generate an example. And then we come through and it does a before and after. So whatever we made a modification to, it would do that. And then we would be able to continue simulating them. So we would save that opportunity into the treasure hunt. And when we're done, it will export a spreadsheet with all of the opportunities in question. Okay. You know, all of the things we just talked about. Power factor correction, not a huge energy savings, but we'll do some other stuff. So it calculates off the I²R values. So if we start saving this stuff, okay, and electricity reduction, generate example, save it, save, and you can see there's a place to put notes. Eventually I will have built up something, and then I can pull that as an opportunity. Okay, so these are all the examples. So total cost savings from those examples or running that simulation. So, you know, here, let's pull up the spreadsheet, and it shows this, and I can put in other information, etc. See if I can get back to the, oh, yeah, let's see, down, and home. Okay, let's do one more, and then we're gonna see if this is finished. No, it has not finished. That is unfortunate. I really wanted to show that, but we will do something slightly different instead. Okay, so let's see, data exploration. This allows me to come through and basically here, let's import an example. Okay. Imported the example data. Next. And it will have, you can see this is from before, so it'll have all of the information in here. And I'm doing a comparison. Okay, and finally it's going to, let's include, oh, guess we'll do that. Finish setup, and then it's going to run an analysis or graphic based upon that stuff. Okay, and where it says apply to assessment, that basically means that, so if I want to come in here and just look at A, etc. Is that consumption? Yes. Yeah, hourly consumption. Okay, it allows me to come through and create more stuff that I can show off or use to come up with things. There's a few other cool things too. Let's take a look at motor. Yeah, this is one. It'll do it. New motor inventory. Motor. Add inventory. This allows me to put in basically, so here we go, dollars, imperial, yeah, 0.1. Didn't update that, did I? 60148. Hit next. Department 1, we'll just leave that there. So in effect, I can add different motors. So I'm going to add a tree. I'm creating a tree basically here. The data that's available. Okay, load characteristics. Let's see. efficiency at different loads. We'll leave that out. Location. So this is the properties we're putting in that we're going to be able to enter. So we'll just keep it at that. So I can come in now and add in that information for the motor or for motors as I build out the inventory. Okay, so let's grab this one here from their thing. So manufacturer, I could put all that stuff in there. And then it'll give me an idea, and then I just keep adding motors to what's there. And it'll keep it up, and it'll give me overall information on what's going on based upon the motor inventory. Oh, okay, yeah. Doesn't have an example. Okay, and then it will go through and it'll run all of the analysis for me, like repair versus replace and everything else. So I can upload this as well. It gives me an example of whatever, but I can run a complete motor inventory in here and do all of the analysis. Where was the one that I was looking for here? There was try this one here. Want to do this? We can put this in an inventory, the head, everything else. Okay. So we're going to use the standard motor, standard pump speed, water, I've got all that here. Motor horsepower, 100. Motor RPM, 1785. And full load amps, what do we say, 121, just for fun. Okay, fine, 114, there. You can see that it, if I don't know, it's going to estimate the amps for me. And then I can come in here and start putting in, I have no idea, flow rate, 50 gallons per minute, too small. Okay, so let's go 110. You can see that it has helpers, right? The head is going to be 60 feet. Motor power in kilowatts. Okay, so let's say 75 kilowatts. And here it's starting to calculate things already. And then to explore the opportunities. Put in a VFD. Install a more energy efficient motor. Let's go to a premium, etc. And then view the report, and it will have outlined everything. It'll give me different graphs. We'll also do a sand key, which is always fun. These are always great in a PowerPoint, right? And then, yeah, I can have saved all of that, and you notice that I can print this directly into a document. Okay, so that is kind of an overview. I'm going to recommend you, if you want to try it, download it, play with it. There's a lot of examples built in. The user manual, here it is quite easy. I did do the online thing. You can see there's only a handful of pages on here with examples. But the other bit is I did go ahead and I tried to look at the YouTube on MEASUR, and they made it quite complicated. It's not complicated. It's quite straightforward. So you can do different assessments, inventory, etc. You can do multiple plants if you're a consultant. I've used this as a consulting tool, etc. Okay, so let me see if this ever finished. It did not, which is really, really, really not good. So let's get rid of it. Let's see if I just open it again and I'll just show you what the features are without it doing all that stuff. I think it's just because of it's pulling stuff down from a website. May or may not be there. And it looks like it's trying to do something. And then last but not least, we are going to, I'll show you how to do it. You come in and you say US EPA emissions calculator. And there we go. Greenhouse gas efficiencies calculator. It'll even allow you to do this. If you are somebody who wants to put this on the website, on your website, just get rid of that. You can see down here, I can put information in and have it calculate, and it'll open up this page. So the EPA.gov energy greenhouse gas efficiencies equivalencies, calculator. Put in energy data or emissions data. So you want to do energy data. Let's say, so this is what's important. So kilowatt hours avoided versus kilowatt hours used. These are two different values. So if I put in kilowatt hours avoided and I put in 1,000, this is all new here. So 60148, which is mine. I can convert the data and it's going to tell me 0.881 metric tons of carbon dioxide per megawatt hour, basically. And then if I, that's high. And if I do it here for used, you can see that's 0.478. That's that value we saw in MEASUR. So this allows me to go through and let's do an example. So let's say I do something and I measure before and after, and I reduce my losses in a machine because I replace the belts, and I take kilowatt hours before and after, and I reduce it by 8 kilowatts. So 8 times 8760 is 70,080. So I divide that by 1,000, and that gives me megawatt hours of 70.8. So I come in here and I say 70.8, I'm sorry, 0.08 megawatt hours. Oh, that is kilowatt hours. So I put in the whole, put in the whole 70,000. Sorry, my bad. 70,080. Don't want it to be low. So 70,000, we're going to have made an improvement that improves my energy consumption by that much. Turn this back on, I think. There we go. So I improve it by that much. This is my zip code here. So now I convert that information, and that'll tell me that it's the same as 14 gas-powered vehicles. This is always good, in addition to everything else, to produce this information. Now, one of the things that has occurred with the changes between administrations, a lot of stuff is pulled out of this. But here we go. So this CO2 emissions reduction is the equivalent of 7,000 gallons of gas, 68,000 pounds of coal burned, that much diesel, et cetera, et cetera, et cetera. So this gives me equivalency stuff that I can use as part of my reporting out to help management feel better. It's equivalent of 62 acres of forest, and so many seedlings planted, and their growth over 10 years, that kind of thing. So that calculator comes in handy as well, again, because it's a third party. Everything between all three of the programs links up. I'm going to attempt to open that software one last time. Oops, I put it on this side. There's the edge of my thing. Yuck. Let's see if it. Here we go. Got it past that. Because really, I want to show you some of the cool bits on there. Migrating the predictors again. So one of the things that happens when you do something live like this is things can go a little awry. If I was doing this as one of my vlogs, I would have shut down and come back later when everything updated and do it, because there's no point in watching it, paint dry. So I'll just describe a few things here. So it allows you to upload all of your energy consumption stuff. That's electricity, gas, etc. Uploaded into this program, and then you can monitor the impact of all the changes. So if I make energy improvements, if I'm using it to track things like, okay, what's happened during this period of time? Oh, the companies put in energy efficient lighting. Well, I can still separate that out from what the savings were from my maintenance practices. It also directly ties into weather data for your zip code and will import that directly. Why is that important? Because the temperature outside has a direct effect. You have cooling days and heating days, and I believe it uses 69 degrees Fahrenheit as the splitter between cooling and heating days. There's so many degrees above and so many degrees before that kicks in. And that all helps with measurement and verification work, meaning I can have things in there, and as I'm making and recording my maintenance improvements, I can have the overall utility data brought into the software. And what will happen is it will start doing all of my graphs and all of my analysis and everything else. And unfortunately, I should have left the example in there. It's downloading effectively. The example is 4 plants throughout the US, and it'll identify which is the one that is most likely the best one for us to address by overall energy consumption. You can put in units of production and it'll track the energy cost per unit of production, one of my favorites, and a few other things. But I'll have to return to that another time because it's just not wanting to download the data. Yeah, that's unfortunate. So with that, I'm going to ask if there's any other. Okay, so thanks for the links to DOE site and measure, look at, verify. Yep. Yeah. So any last questions? Unfortunately, I wish I could have gotten this one up. It's quite cool, but what is the EPA tool called? The EPA tool is the Greenhouse Gas Equivalencies Calculator. Yeah, got it. Yeah, just search for this or USAPA equivalencies or US EPA emissions, it'll show up. It's quite popular. It does. There is an API. If you have a website, there's the widget right there on the lower right. The other stuff to get to here, just search for US DOE MEASUR. Otherwise, you're going to get all kinds of other crazy stuff. And then for MotorMaster and all the other stuff, actually look it up as Motor Challenge and so on. So with that, I'll wait for one more second, see if there's any additional questions. If not, enjoy the rest of your week. And this recording will be up afterwards. If I can, I'll get that other system running. I'll do a quick review of that. I'll tack it on to the end when I put this out on YouTube versus just on the system. No addition. Oh, yep. Thank you very much. Have a great time. For those who'll be at Reliable Plant, we'll see you there.